let's start. So, how do we compile DPL, right? Our data programming language, right? So we want to define virtual machine instructions, and as usual, we want to define the translation into virtual machine instructions, and then we also want to define the semantics of the virtual machine instructions as well. And we have actually two parts, which is what we covered, what we started covering in this set of slides. We have data construction and we have exceptions, right? And they're somehow very similar because in catching exceptions, right, the catch statement creates similar bindings for variables as does pattern matching, and it will all come together when we talk about the virtual machine instructions. So we're going to introduce a few new instructions. The first one is load constructor symbol. All right, and it has 3 arguments here. Actually, the first one is optional, and we're going to see examples where we don't use it, and I'm going to try to explain a little bit later why it is not important. So the X, which is the symbolic name, we add it here so that we make things clearer, and it's clearer what we are translating, but we can throw it away. It's not really useful to the execution of the program. I is an index corresponding to that constructor within its type. So if you remember, for instance, the constructor, the definition of the list, we had nil and cons as constructors, right? So one of them is going to be index 0, the other one is going to be index 1, right? The compiler automatically will enumerate all the constructors within a type and will give them values from 0 to whatever is the maximum, and that particular index is the I, all right? And then n is the arity, right? The constructor has a number of arguments. So for instance, nil has 0, cons has 2, all right? And the rule says that if S is a valid virtual machine program, then LDCS with all those arguments dot S is also a valid program. All right, making thus the LDCS instruction a valid instruction for our machine. How do we use this instruction? We use it in compiling constructors, right? Constructed expressions. So we remember that if E1 up to En are valid expressions, then Ci, some constructor Ci applied to these expressions is also a valid expression, right? Where the arity of Ci must be n. So now, assuming that E1 translates into S1 and En translates into Sn, right? We're going to have that the constructed expression C1 E1 up to En translates into S1, right? Which is the translation of E1 up to Sn. So we enumerate all these translations, followed by LDCS of Ci, I, and N, right? And this is not a surprise, because as we did previously, Ci is just an operator, right? So as we did previously, we are pushing all the arguments on the stack first, right? We are executing the arguments. Their results end up on the stack, right? And then we're expecting that LDCS will pop its arguments from the stack and push back the result. And now it becomes apparent that the stack will have to be able to contain a new type of object, which is a constructed data object, right? So we have integers, booleans, functions, and data. All right? This is very much equivalent to a structure in C, right? The fact that we are naming it Ci is not really relevant. You can think of what data is when it goes into the stack is just a sequence of values, It's a tuple, right? And we're not so interested in the name. Why are we not so interested in the name? It's because at this point, type checking has already been performed, right? We've done the type checking. We know that we are always, for any expression, we're using the constructors within the type of that expression, right? And therefore, CI as a name is not really interesting. Right? CI is fully identified by I within its type. Does it make sense? All right. So, how do we execute this instruction? All right. Well, we have to represent somehow this this value, which is the constructed data. So this is what we're doing. This is what we're doing here, right? We have to you have to say somehow that that's the data, right? So this is essentially a blob of memory, right? A tuple where the first value is the index of the constructor within the type, all right? And then we put all the other values one after the other, right? And we have to, inside the stack, we have to differentiate this from all the other kinds of values that we have. So we put the C in front because it's constructed, right? So this C is just a marker to say that inside the stack, this is a constructed value, right? It's just a convention of representation. Is that clear? So don't mistake this for the CI that would appear in the program, right? Here we only talk about virtual machine instructions, right? And we pluck out of the air a notation for data, which starts with C. Now notice that in this expression right here, CI doesn't appear. The C index I, which was the name, the symbolic name of the constructor, doesn't appear. This is the reason why it's missing from here, and it is completely optional. Okay? So to be more precise, all right, let's say we have two types, type A and type B. So type A has a constructor A1 and constructor A2 with some arities, and type B has constructor B1 and constructor B2. All right, we have done already type checking, so we know for sure we are not using a B where we should be using an A. All right, now what's the compiler going to do? It's going to say, oh, this is the set of constructors for type A. So one will have index 0, and the other will have index 1. And the order is going to be completely random. So I'm just going to say this is 0, and this is 1, right? And the same thing, it will gather all the constructors for type B and say, oh, this is the set of constructors for type B. So let this be 0, and let this be 1, okay? And I know that whenever I have a construction, right, whenever I have an instruction like this, all right, within its type, within type A or type B, this index is a precise identifier. And I actually don't need to know the type at this point. The type checking has already been done, right? So I don't need to know the name. The identifier that I use here is sufficient information to differentiate between constructors. The only problem that I'm going to have from this point on is to differentiate between constructors. I'm going to have the pattern matching instruction, right? I'm going to have the match, and then I'm going to have a pattern for B1 and a pattern for B2, right? So I have to be able to discriminate between B1 and B2, which have indices 0 and 1, and therefore that's sufficient. I will know for sure that at that point it's either B1 or B2 if the type is B, or A1 and A2, because the type checking has been completed. Does this make sense? So we really don't care about the name of the symbol right here. Then that name is converted into a number, and within its type, we start from 0 all the time. Okay? Does this make sense? And now the C that I have put here is not really necessarily the most fortunate notation, but that C is different from all the CIs. It's in the virtual machine space, and it just says this is a tuple of n plus 1 values, the first one indicating the constructors and the rest indicating the arguments. So cool, right? So now at the top of the stack we have constructed values, we can have functions, we can have integers or booleans. Okay, and what happens is exactly what used to happen whenever we had any operator. We pop n values, and we push back this new value that represents the data construction created with constructor I of whatever type we had there at the time of doing the type checking. Yes? Cool. All right. So the interesting thing is that what we call pattern matching in functional programming is a switch statement in Java or C or C++ or JavaScript or any other procedural language, right? So we're going to be procedural at the level of the virtual machine and introduce two new instructions called switch and end switch. The switch denotes the number of branches. So if we're trying to pattern match on a type with n constructors, we will have n branches, right? We will have separate cases, and that argument of n has to be there. And then we have an end switch instruction that takes an M and an L. So the interesting thing that we're going to notice when entering a switch statement, a switch construct, is that we need variable binding, right? The pattern, let's go and clarify this. So let's go to one of the examples that we have discussed last time. So this is an example, right? And we have pattern matching right here, right? This is pattern matching. And if you look here, if we take this expression in isolation, y and ys are free, as is f, right? So y and ys have to receive their bindings from somewhere, right? There will have to be an environment telling me what y and ys are. And you see, the bindings come from here. I think we talked about this last time, and hopefully you remember it, or you're getting a refresher now. Right, is this clear? F will be bound from here, but y and ys will receive the binding from the pattern. Right? So, going back to our slide. All right? And switch is going to be a very interesting kind of instruction. It's a go-to, right? So we have a label, and execution will go to the label L after as part of the execution of end script, right? So the program counter will go to label L. But at the same time, since we're exiting the switch, we have to undo the bindings that we have created at this switch, at the point of entering the switch, right? And how do we create or remove bindings, right? We extend the environment with a certain size. Remember? And then So the environment now is an array. We don't go from variable names to values. We assign numbers to those variable names, and we're going, it's a simple array. We're going from indices to values, right? So whenever we enter a switch, right, there's going to be a number of variables in the pattern. We're going to extend the array right at the end by that number, and we simply need to reduce the size of the array by the same number as we exit. So that number will be the number m. So it's an interesting kind of goto. Goes to L, but in the process reduces the environment. All right, makes the environment shorter. So that's what's going to happen, and it's all going to come together at the end as usual. All right. So how do we translate now an entire match statement? So remember the syntax. We have the keyword match. We have the expression to be pattern matched, E, and we have a number of clauses of the form pattern, arrow, expression. Okay, we have n of them right here. So these are the clauses, pattern, arrow, expression. So if E matches pattern I, then we're going, the entire thing evaluates the expression I, right? So how are we going to do this? So let's see what the translations are, right? E translates into S, that's our assumption. And then we're going to have this triple here. We're saying, and this is going to be a helper as we did before. We're saying that the triple P1LE1 translates into L1S1. What you need to understand at this point, we're going to define this later, but what we need to understand at this point, that in fact E1 translates into S1. All right? And we're going to define this later. And then, as part of this translation, there is a label L1 here, and I took a shortcut, and inside here I haven't shown the label, but think of the label as being prepended to S1 up to Sn. So L1 prepends S1, Ln prepends Sn. Okay? So we're assuming that this is EI translates into Si, and each Si has a label. So here's what's going to happen. We're going to evaluate S, right? The result, which is the translation of E. So the result of E is going to be at the top of the stack, right? When we enter this, all right, we're going to jump to the current location plus the value of S. So this S we essentially want to be a number, right? So this switch N says, oh, these N locations are special. And when we enter switch N, we're going to go from this point somewhere inside to a location dependent on the value of E. Does it make sense? The value of E is at the top of the stack. Now, let's look at what we have here. You can think of this as an array, right? It's an array of instructions, right? So what's going to happen? The switch is going to take me to index I, and whatever I have here is go to Li. Go to Li is somewhere in the middle, and it is precisely the pattern that matches E. All right? Does it make sense? Yes? No? So again, this go-to, think of it as an array. Okay? Let's do the drawing again, because it's too much drawing, right? Think of this as an array. So this is index 0, and this is index n, right? minus 1. This switch instruction is n, yes, because I need the size, right? I need the size of the array. The n tells me the size of this go-to array, this array of go-tos, right? That's why I have it. But this switch is going to look in the stack, which is the value of s, right? And based on that value, is going to jump somewhere in the middle. So it's going to go, let's say this is PC, it's going to go to PC plus I. What's at PC plus I? Go to Li, right? Go to Li is going to send me to Si. Si is Pi Li Ei goes to Li, sorry, L here goes to LISI, right? So this E matches exactly Pi, right? Which means that normally I should execute EI, I should execute SI, and this is exactly what is happening, right? So this is a very clever way of treating code as data. I have code, a sequence of n go-tos. I look at it as an array. I perform an indexed jump. And from there, I can go further to select the code that I have to execute. All right? This does what? Performs the matching in constant time. What would be the alternative? If matches P1, execute P1. Else, if matches P2, execute E2, right? If matches P3, execute E3. And if you happen to have the bad luck to match Pm minus 1, then it takes n steps to get there, right? Whereas in this case, it takes constant time. Does it make sense? Yes?
How do you differentiate this? Like in C++ switches, you have a break, or sometimes you don't have a break and it falls through.
Oh, so at the end of SI, so whenever we see the translation of this guy, we're going to see what happens at the end of SI, right? At the end of SI, I'm going to have a jump to L. That's why you have the L here, right? So I pick a fresh L, I make it part of each of these individual translations, and in this way I make sure that S1 up to Sn, each of them have a go to L, right? And actually I can't have a go to L because I also have to shrink the environment. So I'm going to have an what was that? Switch, an end switch that goes to the end, right? So in this way, I am going to skip the rest, right? So this piece of code, S1 up to Sn, is laid out like here as a sequence, right? So I have S1 here, and there's L1 at the beginning, right? S2 is here. I have L2 at the beginning, right? And what happens? I execute L2, let's say, and from here I have to jump and skip everything else, right? So somewhere here I'm going to have L, and in each sequence I'm going to make sure that at the end has the end switch, right? So this translation, which is a helper, will make sure of that. Does it make sense? So we'll get there. But before we get there, let's look at a clever optimization. Okay? So what I did here is, instead of putting here go to ln minus 1, I've changed the order. I put Sn here and S1 up to Sn minus 1 here, right? So then for the last step, it executes faster, right? I don't jump twice. I jump from here, right here, where previously there was a go to ln, right? But now I can start executing the last branch. And this, well, I mean, it's a minor optimization, right? But saves one instruction, right? So the code is shorter by one instruction. And it also, in that particular case, it's faster by not having to jump twice. Cool? All right. So these kind of optimizations are very commonplace in compilers, right? When we talk about compiler optimizations, this is what we're talking about. Each optimization gains very little, but overall the gains are pretty significant, right? If you apply these very, very small optimizations, one after the other, after the other, after the other, in the end you can end up with code that executes tens of times faster than the original. Cool. So let's see how we translate a triple. How we translate a triple into machine code, right? So we had this weird construct, this triple here, right? So previously this used to be a pattern. This was pattern I, right? But pattern I is constructor applied to variables, and these must be free variables. We're actually introducing a binding. These v1 up to vm are new variables, right, that will be referred to only in SI, right? v1 up to vm appear free in SI, and we're trying to provide a binding, sorry, not in SI, in EI. And we're trying to provide bindings for those variables, right? And let us assume that EI translates into SI. And we're wondering if we have this triple PI L2 EI, what should these translate into so that the whole thing closes with respect to what we saw on the previous slide? All right? So what are we going to do? Well, this label here that was coming from before, this is going to label every single translation of a triple, right? So this is the label that comes at the front. Notice that this label is not part of the triple here, okay? Then we're going to have the SI from here. We're going to just copy it over, and then we're going to end with, as I was saying before, the AND switch. All right? The AND switch will jump to L2, right? This L2 that was provided here. This is the L2 that we want to have way at the end. So the AND switch is, in essence, a go-to. But as we enter the switch, and we're going to see the translation, we're going to see the virtual machine execution of the switch, right? The semantics of the switch. We're going to see it shortly. And we're going to see that at that point, we have to expand the environment, right? So what happens at this point is that we have to reduce the environment by m locations. And this m is specific to the clause. Each clause will have a different m. Each clause has a different constructor with a different arity. So the branch has to end with a AND switch that has a different m here, corresponding to the pattern that was on that clause, right? This v1 up to vm will be different for every EI. Does that make sense? So let's make sure that it makes sense. So as we go here, right? So this is of the form C1 V1 up to VK1, right? And for P2 or Pn is going to be Cn V1 up to VKN, right? So this K1 and Kn are different numbers. Each of these clauses has a different number of variables in the constructor, right? So the corresponding AND script has to reduce exactly by that number. Make sense? So is this pattern clear now? So let me repeat again, right? So this S1 is this guy. Right? So what we have is a sequence of these guys, right? So I have a sequence of these guys, right, followed by another one. They have different length. Each of them is the compilation of EI. Each EI will compile into a different length, right? But then, right before here, we have an array of goTos. So this goTo will send me here. This goTo will send me here. This goTo will send me here, and so on, right? So because this is a regular array, every element has the same size, the switch instruction can go to the right goTo. And the goTo will go there then to the corresponding branch. Clear? It is essential in here to have a array of elements of the same size. The same size is very important there, right? Now you could do an optimization to this as well, which is very widely used nowadays, right? Because memory is cheap. So instead of having an array of goTos, you translate all the SIs, right? And then each of them will have a different length. And then look at the longest of them. All right? So memory is cheap. So I'm going to create an array where each element has the size of the longest. Instead of an array of goTos. So some space here is not used. Some space here is not used. I don't care. I might even waste more memory because I'm going to say, oh, let this be a start of a page, of a memory page, right? And then let this be another start of a page, right? Because why? If I do memory swapping, I don't want two swaps. I just want a single swap. And if I do caching, right? Caching always starts at the beginning of a page. So I make sure that the full execution, I don't need to go through two cache lines. I can go just through one. Does this make sense? So we are saving time, right? We are saving time in many ways, right? There's only one jump for each branch. Then each page starts at the start of the cache, so there's faster page swapping and faster caching when needed. And actually, that's very standard practice. Cool? Is this understood? So it's a trick that I don't think you have to mull over a little bit, and you should have the opportunity to ask questions if you need. Okay? So yet again, is everybody okay with it? Does everyone understand it now? Cool. So let's see how we execute the switch.
Okay.
Yes.
So like initially it was the goTos arrays which arguments of the same length, right?
Yeah.
And then after you say that further optimization is you can just put it all, like there can be extra space that is not used. Do we still use the goTo arrays? The goTo.
No, the goTo is not there anymore, right? So yeah, so every instruction here is replaced by a sequence of instructions, right?
Mm-hmm.
That, but I'm going to reserve for that sequence of instructions as much memory as the largest of the branches would fit, right? Because the essence for this index jumps is the same size, right? So then the S1 goes in here, the S2 goes in there, right? And the index branches just does that, right? And of course we're simplifying because this switch is going to do at the processor level. This switch is going to do what, right? Instructions are never 1 byte. So you actually have to look at the size of a goTo in bytes, and you have to take whatever number comes from here and multiply it by the size of a goTo. So that always needs to happen. right? Instructions or 1 byte instructions are very rare. And then if you're multiplying, so most jump instructions, if you look at the Pentium, the most common one is 5 bytes, right? Right. So now you're going to have to multiply by 5. So if you're going to make this, let's say 8K, 8 kilobytes, you're going to have to multiply by 8,192. There's no difference, right? What's multiplying by 5 or multiplying by 8,000? It's the same amount of time used for multiplication, right? Actually, multiplying by 8K might be faster because you can do a shift, right? You can do a shift by 3 bits instead of a real multiplication, and that's faster. So it might be even better. Understood? Yeah. All right. So semantics of switch. So what do we expect in the state of the machine when we have a switch? There must be a construction, a piece of data at the top of the stack, right? It does make sense to have a integer or a boolean or a function. The only way the switch would work is if at the top of the stack there's a constructor with some arguments. Okay? So then what is going to select the branch? The branch is going to be selected by this I, because I want to jump to the clause corresponding to the ith constructor, right, within the type. So this I is going to give me the branch. Is that clear? So it's essentially a jump instruction. We just go to PC plus I, right? It's an indexed jump. Okay, and these instructions are available, right? There exist even more general instructions at the level of the processor, because you can jump to the address contained inside any register, right? So I can take a register, I can do some computations with its contents, and I can just jump to whatever is inside. All right. Now, this is not the whole story, because these are free variables that have to provide bindings to whatever is in the expression corresponding to that branch, right? We have pattern I, arrow, expression I. Expression I mentions these variables, all right? And they have to appear in the environment. So we're going to extend the environment with slots for these values. All right? And remember, variables don't need names anymore, right? So we are looking at the variables, enumerating them, and saying this is index 0, this is index k, right? So whenever we're manipulating an environment, we only have to add locations to the end. And whenever we want to remove variables from the environment, we always have to reduce the environment array by a certain amount. We just have to shorten it. That's enough, right? So these variables are now in the environment. And then as I go into executing the branch, I'm going to have values for these variables. Clear? The runtime stack stays the same. Nothing changes there. All right? So execution moves to the branch, and we'll continue executing from there. Is this clear? Yeah, cool. So what needs to happen when we have AND switch? Remember, AND switch has a number M and a label L. And it is largely a go to L, right? Because when we reach the end of the branch, we have to skip all the other branches. Okay? So, therefore, that's what's going to happen. PC is replaced by L. right? Now, there's this added thing of reducing the size of the environment. So we're assuming that we have an environment that has at least m variables, right? So it's an array whose last m slots exists, are there, and what we have to do is discard them. So we're going to move to an environment that doesn't have those anymore. It's shorter by m locations. Cool? All right. So any questions so far? So think a little bit about the whole thing, because we're going to move on to a separate topic. So if you have any questions, please ask. You see, when you think about compilers, it's always a very interesting exercise in abstraction, right? Coding is like Lego toys. They have to match. What you want really is something that has straight sides, right? But you can only build it from things inside that have jagged edges, like a puzzle, and they go together, right? So if you look at the two things, switch and AND switch, right? So there's the expansion of the environment and then the reduction of the environment, right? To obtain a program that has no free variables in the end, right? And then the way the translation of this thing works, right, is the same, right? It's like I'm putting some jagged edges on this, and I'm leaving some jagged edges here, so then they go together and they match, right? So you have to do this all the time. You have to invent these little helpers so that everything comes together. All right? So if you do this frequently, and if you develop a habit, then your coding skills are going to improve tremendously, right? It's a bit of a challenge in the beginning. So hopefully you're getting that. Okay? So shall we do the try catch? Shall we do exceptions? All right, so the catch is not very different from a match, right? So the try part evaluates an expression, right? And that expression may result in an exception or not, right? So you're thinking that, what is the overall value of the expression I'm evaluating? If it's an exception and it matches the catch part, and then I have a variable in that catch part that has to provide a binding to the catch clause, right? So that's very similar to a pattern giving value to the expression and the branch, providing bindings for variables in the expression in the branch. Okay? So we're going to reuse the AND switch. The AND switch is a very useful operation right now. We don't have to come up with a different one. All right? So we're going to introduce new instructions, and they're relatively simple with what we know now. Right? We're going to have a try instruction that has a label, and it's essentially a way to record the fact that if an exception occurs, we want to go here. All right? So the interesting thing now is we can't process that L right away. So we have to store that L somewhere so that it can be used if the exception occurs. All right, and we're going to see how that happens. But essentially, we're going to put this L somewhere, and then if the exception occurs, we know where we have to go. Okay? And then, if there's no exception, notice that this is E1 that is the main code that we want to execute. So if this translates into S1, so if this executes correctly, then we have to skip all this thing. We have to skip the catch. So we're going to have an end try that on one hand jumps where it's supposed to jump, so it's largely a jump instruction, but the other thing is wherever this label was stored, that storage has to be undone, right? And then let's say an exception did occur from inside here, and we're going to have a mechanism. So it's going to use the runtime stack, right? Because we know how we can, what we have how whenever we return from functions, we have a pretty similar kind of mechanism. So it's going to be somewhere in the runtime stack, right? So let's say I execute S1, exception occurs, right? So somehow when that happens, I'm going to jump here. Well, what happens naturally? I execute S2, all right? But S2 will have a similar kind of translation like the triple that we had previously, right? Because it has to end with something that, it does end with something, so we have it here, right? So it will execute S2, but we have to provide a way to expand the environment, all right? So we have to do that. And we reach the end, and this is the end switch. And what we do here is we have to skip to L2. And it so happens that L2 is right there, so there's no real skip necessary, but it doesn't really matter. And we only have one variable, if you remember our catch. Our catch format is catch one variable that is an integer, right? So what we have to reduce the environment by is the value 1. We have to reduce it by one location. That location would correspond to the catch variable. All right? So having this pattern, let's define everything else so that it fits. All right? So we're going to have to provide a definition for try, for end try, and that's it. Okay? Oh, before we get there, we also have the throw instruction, right? And the throw instruction is just translated into throw. And this would be the correct form. Oh, no, sorry. S dot throw, that was correct. Very sorry. We're not so what I'm not doing is defining the syntax. I'm defining the translation right away, right? So what happens is that the value of E needs to be evaluated, and for that we execute S, and as we execute S, the value goes to the top of the stack, right? And then we throw, and that's the value that has to go into the variable in the catch. So now let's define everything so that it matches. It matches together. It goes together. So let's start with the try. Okay. We are going to expand the runtime stack by this very weird element. All right, so this is now, so the runtime stack before the execution is here. This is the runtime stack after the execution, right? And there's this weird element here. All right. So the runtime stack stores the entire operand stack. All right? And you're going to ask, how is that possible? Isn't it going to really blow? So the operand stack, from this point on, as we go into executing the try part, is only going to grow. So if I just have a pointer or reference to the point in the current runtime stack, if I have the current stack pointer, that's sufficient. The stack is not going to shrink, it's only going to grow. So I'm not going to really store the stack in there, I'm just going to remember the current stack pointer for the operand stack. And we're adding this marker of -1. Think of it as just a marker, right? -1 applied to OS, showing that this is the exception marker. All right? We're going to store the label L so that we know where to go in case the exception occurs. Right? Remember, we were saying we have to remember the L. We can't make use of the L, take advantage of the L right now. We can't jump right now. We have to put this away for the time when the exception occurs, and only then can we make use of this L. And we're also storing the entire environment. All right? And again, the environment is only going to grow. So all I need to store, and the environment is an array, all I need to store is the index at the end of the array currently, right? And I'm going to be able to restore it. All right? The reason why we're storing these things is that we want to restore them in case the exception occurs. Okay? You were here, right? So the -1 denotes the try-catch frame. It's just a marker, right? One thing we're going to see is that we're going to keep popping until we find the try-catch frame. That's going to be one operation. So what happens at the end try? When we reach the end try, if we ever reach the end try, it means that the exception has not happened. Right? If the exception has not happened, what I need to have is the try-catch frame right at the top of my runtime stack. So I have gone inside the try part of the statement. I have gone into many functions, but everything has returned nicely. So I have the same stack frame, runtime stack, as at the time of beginning the execution, right? It must be the case that the runtime stack has the try catch frame at the top. So what do? Just discard it. We go here, and it's not there anymore. Right? So this is the very simple case. We were prepared to handle an exception, but the exception didn't occur. So all the preparations that we made have to be thrown away. Is that clear? All right. So what happens if the exception does occur? So the exception can occur in a variety of ways, but let's just assume that it happens when we encounter a throw instruction, right? So how is that, right? We have a try, we have a piece of code, we have a catch, right? And from here we call a function, and from here we call another function, and somewhere here we have a throw, right? And what we need to do now, from here we have to jump right after the catch, right? And in the process we have to bind the catch variable. Is that clear? So what happens here is we're going to keep popping, right? And it's very easy to say we're going to keep popping, but in fact, to represent that, we have two rules. All right, we have a rule when we have encountered the throw and the current runtime stack frame is not a try-catch. So when I say it's going to keep popping, I'm going to apply the rule again and again and again, and at each step I'm just going to discard this. Right? So again, let's draw the picture. Catch, go to a function, go to another function. So when I'm here at the throw, what's going to happen? Well, I'm going to have a stack frame from this call and a stack frame from this call, right? But if I want to go back right here, what happens with these two? I have to throw them away. I don't have any use for them anymore, right? Because all I have to do now is with this throw, I just want to go back here. So I have to get access to the stack frame that gives me access to this point, right? So I'm going to look at this stack frame. Is it try catch? No, throw away. So I'm going to go to this one. Is it try catch? No, throw away. I'm going to go to the next one. Oh, is it a try catch? Yes. In that case, I know the label where I have to go. That's going to tell me the label, right? So for the first two cases, we're going to apply the first rule. Whatever I have here, I just throw away, right? You see, the PC doesn't even advance. We are still on the throw instruction, and the state of the machine changes by just throwing one stack frame away. So I'm going to throw one away, and this one, I'm going to throw another one away because this rule still applies. This is still not a try-catch, so I'm going to throw away this one. Oh, I reach here. At that point, I'm going to be in the case of the second rule, right? At some point, this will not apply. This n not equal 1, minus 1 will not apply, right? So I'm going to be here noticing a try-catch stack frame. And what do I do at that point? Well, if I am here, what do I need to be having at the top of my operand stack? Well, remember the instruction in the language. This is the instruction in the virtual machine, but in the instruction in the language is throw E, right? So this E was evaluated before this virtual machine instruction, and the result of E is at the top of the stack. It has to have this form. All right? It has to be an exception, otherwise the machine is in the wrong state. So at the point where I encounter a stack frame in my stack, the operand stack must be having a exception value at the top. Otherwise, it doesn't make sense. Okay? So I'm going to use this I to create my binding here. All right? I'm going to expand my environment by one location. All right? And then I am going to use the value of the label. All right? I'm going to use the value of the label as a place where to go, meaning that I'm going to jump from here, right here, which is what I saved when I executed the try, right? And then what environment do I want? I want the environment that I had at this point. So going into a function, I have added some variables to my environment. And going into yet another function, I've added more variables to my environment, right? Those variables are no longer in scope. So I have to discard them. So I'm going to drop this E completely, and I'm going to use it here. And this is what I expand by one location when I move back to the catch. right? And once I have reused all these variables, I can discard this record and I can keep my current runtime stack. Okay? So this is what really happens. I'm going to keep popping from the runtime stack until I find the try-catch step. Now, one thing we don't have in our current setting is the finally, right? And the try-catch originally, the way it was designed, didn't have a finally, all right? But then resource management came into play. So it turns out that resource management is very difficult. Whenever your program manages resources, you have to acquire the resource, and as you use it, right, for a while, and then you have to relinquish it so that other parts of the program or other processes may use it, right? So it's very important that no matter what your program is doing or is going and what kind of errors it's going through, the resources get relinquished, all right? So it was especially difficult to do it in the try with exceptions, right? So the solution to that was to add a finally, and then finally is a piece of code that executes no matter what. All right. So this popping off the stack frames from the stack will give you a chance to restore the environment of the previous function and potentially execute any finally statements that you have. Right. So how would we expand this to finally? Well, every time you pop a stack, you're in the throw, right? Every time you pop a stack frame, you have the label of the return, and you try to go to the return and see whether there's a finally there, right? So you may have a try without a catch, but with a finally, which enforces code that needs to be executed. All right. So that's the reason why we're popping one by one. Otherwise, what could we have done instead of popping one by one? So remember, from this point on, the stack only grows. So instead of putting an entire record on the stack, I can have some sort of a global variable that keeps the stack pointer, and I can just restore that stack pointer. I don't have to go back one by one by one, right? I can do a constant time operation. And this is actually, in fact, how the original exceptions were implemented, right? But it wasn't a good solution in case the finally would be added to the language. Does it make sense? Cool. Oh, and this is it for the current lecture. So cool, we can move on to the next set of slides. So, perhaps the part that you expected from the very beginning, right? Imperative features. So, what are the imperative features? Mainly assignment, right? Once we have an assignment, we can also have while loops. While loops make no sense without assignment. All right? So at this point, we can introduce while loops as well. Okay, and this is not the way we went so far, right? We made kind of a point that values don't change once they have computed, they never change. That doesn't bother us much, right? We know that with recursion we have no problem producing repetitive computation, right? And there are certain advantages from not having assignment. Apart from the fact that it's good for formal reasoning and theoreticians Theoreticians like it very much because of that, right? Makes formal reasoning, makes theories about about programming somewhat simpler, right? But they are a major source of bugs. Assignment is a major source of bugs. You will be surprised how much fewer bugs you will have in your program if you very adamantly avoid assignment, right? And modern languages have support for that, right? For instance, JavaScript in ES6, right? You have the keywords val and const, right? So you can define a variable and do not be mistaken. That's not a symbolic constant, right? You're writing const x equals something, right? That's not a symbolic constant because it's a local variable, so you can't have it as a constant. It's something that gets computed every time, but it's something you cannot change later, right? So if a language that is so poorly designed as JavaScript and such a free-for-all, people have figured out that, oh, it's good to have this. It must be very important to try to avoid assignment. Okay. Scala as well, so has var and val, right? So with var, you define a variable whose value can be changed. With val, you don't, right? And the recommendation is always to restrict the number of vars as much as possible, right? All the optimizations are there for you to not really care about that. We have languages in which it's very difficult to have assignment, like Haskell. And even OCaml, it's not that easy, right? So you have to declare a variable that is a reference to a value, and then you can perform assignment with a very clumsy syntax, right? So the language sort of telling you don't do this. Cool, but it's a feature, so we want to know how it can be implemented, right? That's an important thing. So we're going to go still do it in a sort of functional programming way, right? We're going to define a class of mutable values as opposed to the regular values that we can have. All right, and then we're going to define assignment for that. And we're going to have another hierarchy of languages, right? One that can only mutate a value, another one that can mutate a construction. All right, and we're going to keep going, right? Then we can define while loops and so on, right? And it's going to go through the regular workflow, syntax, examples, notational semantics, and further down to compilation, virtual machine, and so on. So the instruction is going to be denoted by this colon equal. X is assigned E, all right? And because we have assignment, the following construct is absolutely necessary, this sequence. We have expression 1 followed by expression 2 with a semicolon, and the value of the entire thing, remember everything has a value, is the value of the last one, will be the value of E2. So E1 gets evaluated, the result gets thrown away. We're going to throw away whatever is at the top of the stack. We're going to evaluate E2, and that's what stays at the top of the stack. All right? So that's, again, very common. We have while loops with the very common syntax. Okay? And this is going to be an example of our new language. Let mutable x be 0 and non-mutable y have the value 3, and we can assign to 1, and we can assign to x, and we can assign to x a value dependent on the previous value of x, right? And we can combine in any expression mutable and non-mutable values. We can say x plus 1. All right? And you see the semicolon, the way it is used there, and we're saying at the end that the value of the entire program snippet is x. All right? And we won't quite need a return statement because of that. We can use it inside functions. All right. And this is a factorial program. Factorial program, so it evaluates to the function that computes the factorial of a number. That's the real value, but uses mutation inside. This computes the greatest common divisor. It's the most basic algorithm for that. Okay. So again, we're using mutation inside a function, and we're also using a while loop here, as we did before. And we want denotational to have denotational semantics, right? So the trick is that everything has to have a value, and what's the value of an assignment? All right, and you can have many choices here. You can say the value of the assignment as an expression. So x is assigned 1 is a valid expression. Every expression has a value, right? So one approach could be that it's undefined. So we define this new object called undefined, and x is assigned 1 is evaluated to undefined. However, x is assigned 1 has the side effect of putting 1 into x. This is what JavaScript is doing, for instance. Okay? And I think also Python. But on the other hand, we can just use the value of the variable as the value of the entire expression. So you might be surprised, but C has this approach, right? So in C, assignments are expressions and they have values. All right? So x is assigned 1 is an expression whose overall value is 1. All right? So we're going to see. Actually, I can't remember. I'm going to open the slide and find out how we evaluate our expressions. All right, but how are we going to represent the denotation of a mutable variable, right? Because previously it was symbol to value. Now it has to be symbol to store. Store being some sort of an entity that can hold different things and whose value can change. All right? So, or a location, right? And then what we call a store is actually the mapping from locations to values. So we're going to have a store that is separate, and if you find that the name of store weird, then you can think of it as a heap. All right, just that it's not quite a heap because the heap requires garbage collection, but it's pretty much what you know as a heap from all the languages that have garbage collection. All right, so this store, one, it has to be a part of the semantic function, right? But it also will have to be part of the virtual machine. So we're going to get to a point where now we have a heap attached to our virtual machine. So we're going to enrich our semantic domains, right? We have a store, and the store is locations to stored values, right? Stored values can be integers, booleans, or functions, right? There's nothing else that is really interesting as a result of an expression, right? Whereas expressible values are things that can sit in the operand stack, so we also have exceptions there, right? Storable values don't contain exceptions. All right, so let's look at store manipulation, right? How are we going to talk about store manipulation? We need some symbols, we need some operators, all right? So now we have environments, And mutable values inside environments have symbol names mapping to possibly location, right? So either values if they're non-mutable, if they're mutable, it has to be location. And then the store will give me the mapping from location further to the value, right? It's a 2 levels of indirection. So I have a store, right, which has a location L that is mapped into 1. And then we have an environment that has the symbol X mapping into the location L. So to access the value of X, I have to do a 2-level of indirection kind of evaluation. I have to apply sigma to delta to X, and that will give me the value 1. All right? So, previously, remember the environment is essentially a crutch, because what I want to end up with at the end, when I look at the denotation of the full program, I want to end up with an empty environment, right? But the environment is this crutch that allows me to handle expressions, smaller expressions, whose scope is not yet clear, right? It's sort of a crutch. But now I also have the store. So the store has to be linked to the environment. But guess what? The store doesn't have to be empty as I evaluate, because the store is essentially the state of the program. So I'm going to take, the program is now sort of like a transformer. It takes the initial store into the final store. All right? So the store is something that is not really a crutch. It really represents storage. All right? But we're going to put it syntactically on the left-hand side of the turnstile. Right? So essentially, we are reading this as assuming this, right? This expression has this denotation, right? And what's going to happen is that the expression has side effects now. All right? So the store changes. So this guy here becomes this guy. Right? So the previous store is no longer the same at the end of the operation, because X may become from 1 becomes 2. Right? And at the end, when I have the entire expression which executes, the store will not be empty. On the contrary, it will have all the values of all the variables inside. All right? So now, what happens is that we evaluate many expressions, right? In the various constructs that we have, and this is one example. So here we're first going to evaluate E1, and then we're going to evaluate E. Both E1 and E have side effects. So we have a threading. What we need now is a threading of the store. So E1, as it evaluates, takes the sigma into sigma prime. Right? And you have to read this as an assumption, assuming that this. So my overall assumption is that assuming that this is true, E1's denotation is this. Right? But when I make the next assumption here, what I have to do is use this guy. I have to thread the storage, the store. Right? So I no longer have completely independent evaluations. Previously, it was a lot easier because I could treat E1 and E in complete separation. I would say, oh, environment here and the same environment here, right? Or the same environment but slightly modified. So now, what can happen is that this store, and this still holds, right? I have the delta here and I have a slightly modified delta here. Delta is almost the same. But I can come in with this store, I get the completely modified store here, and this guy has to be threaded into the input of the next expression, and will produce yet another completely modified store. So I need to have this threading all the time. right? This is going to be a constant concern from this point on. Okay? So what happens here is that as I execute this, right? So it's pretty similar with what it used to be, right? Just that this sigma becomes sigma 1 right here, then the sigma 1 gets fed into E, and it becomes sigma double prime at the end of the expression. Okay? And we will have to worry about this when we translate into virtual machine language as well. Cool? So let's see how we handle mutation, because this is really the interesting case. All right? So let's assume that when evaluating E1, we're taking this sigma into sigma prime. Okay? What do we do next? We take this sigma prime that we obtain at the end of E1 and we have to expand it with a mapping for some L1, right? And we're always saying let L be a fresh variable. If you think in real terms, what do? We allocate space for a variable, right? We say variable equals new something, right? All the time. So that's what happens, right? A new location is created inside a store, inside a heap. And what do we put there? This value that we have just computed. Because that's what happens, right? This x1 lives inside here. So whatever happens, actually it doesn't live inside here, it lives inside the sigma that was obtained at the end of E1, right? So we create a location for that, we store the value of x1 in there, and then we can go ahead and execute E. All right? And what do we obtain at the end? Well, see, we were making the assumption that L1 is already here, right? So we were taking sigma prime, that was our assumption. And we have already added a location for V1. And under this assumption, the denotation of E is V and sigma double prime, right? So even though this is sigma, the semantics of let says create a value for x1. So what we're going to have here is not this guy, but rather this guy. And then as we execute E, we're going to end up with sigma double prime. So everything matches together. Okay? So this is telling us that execute E1 or evaluate E1, get the new store, expand the new store with a location for the value of x, then execute E with that and get a store that is sigma double prime, and that's part of the notation of the entire expression. Okay? And by the way, so x is still inside there. The location L still exists, right? The location L1 still exists in there. The mapping from x to L1 doesn't exist anymore because it's out of scope. Is that clear? So this mapping disappears. This mapping, so this disappears when we're here, right? This one stays there. All right? We never delete anything from the store. Store just grows, right? And in real life, what happens is, at some point, we're going to look at stuff that is no longer used, and that will be garbage collected, right? But we're not talking about garbage collection here, so in everything we do, the store always grows. Everything will stay there. All right. What happens for immutable values? They don't affect the storage, right? So x is a variable. X is a valid expression because of that. What's the denotation of x? Well, we have to adapt to the new setting. So we can't evaluate x just with the delta. We have to evaluate it in the context of a store and an environment, right? And what are we going to get? Well, the value is whatever the environment has. X is immutable, remember, and the store is untouched. So this is one operation that doesn't touch the store. What happens for a mutable variable? So x being a mutable variable, right? X is a valid expression. So what are we going to do? We're going to apply the two level of n directions and get the value of x. That's going to be the value of the expression, and the store is again untouched, right? It doesn't really change in any way. So one interesting thing is now assignment. All right. So when we have assignment, the only thing that changes is the state, the storage, the store. Okay. So x is a symbol, and it must be appearing in the environment, right? Otherwise, we can't make an assumption. We can only talk about this as a valid expression if x already appears here. Doesn't make sense otherwise, right? But more than that, because x is mutable, whatever the environment maps to has to be inside the store. So x maps into a label, a location, right? That location must exist into the store. Otherwise, we can't proceed with this. So let's now assume that under the context of sigma and delta, the denotation of E is a value V, and what we get after the evaluation is a new store sigma prime. Okay? So what happens if we assign E to x? Well, E will evaluate independently. This guy just evaluates, meaning that the sigma prime is produced no matter what. Right? When we put the value of E inside x, which store changes? Sigma prime, the one that was produced after E, right? This is the sequence. First evaluate E, and I have no choice but to accept the sigma prime. So only that I can modify in order to produce a value for x, right? So then what is going to happen is that I'm going to take this sigma prime and I'm going to create a mapping from the current location of x. The location doesn't change, but the value stored at that location changes. So this expression tells me that I change the current value of x. I change the current value at the location that x maps into. I change that to v. Cool? So let's look at an example. Right? We want to assign a to 2. Right? Obviously, this only makes sense if the environment has a mapping to L, right? So this is my environment, and how do I create an environment whose only mapping is A to L? Well, I start from the empty environment and I modify that to have a mapping from A to L. And how do I create a store whose only mapping is from location L to value 1? I start from the empty store and I change that to have, right? So this expression is very convenient. It makes it very clear that that's an environment that only has a mapping from L to 1, right? So this is just for the purpose of providing an example. We're assuming that that's our starting point, right? A store that has a location that stores 1, and an environment that has a variable that maps into L. And we try to assign 2 to that value. What are we going to get? We're going to get, as an entire value of the overall expression, we're going to get 2. So now I'm actually finding out that of the 2 choices that we had, we're going to accept as a value of an assignment the value of the expression, right? So the value is 2, and the store, right, is 1 that is produced from the previous one, from this guy, and has a further modification of L storing 2. Is that clear? So this is a store that first stores 1 into L and then stores 2 into L. Obviously, algebraically, this is phi L2, right? So if you look at the algebra of stores, of store changes, I can just disregard this one, right? But just to be faithful to the rule that we put on the previous slide, syntactically, this is what we obtain, right? So we obtain a store that's which stores at L the value 2. Is this clear? Cool. All right. Function definition. So again, the important thing is threading here. We're going to take this rule. This rule doesn't explicitly change anything, right? But with the evaluation of every expression, the store now changes. I have to add a store to every evaluation, and the store now changes, and I have to be careful to thread it, right? So I want the function definition, right? And evaluating this function with an initial store produces a new store. And now I have to be careful to feed the store in the right place. Because I think this one is not sigma prime, it's just sigma. The second one is just sigma. Yes, so this sigma prime is actually sigma. Sorry for the typo. All right, so what happens here? Well, first thing I'm going to evaluate is E. So whatever I have here, I'm going to evaluate E first. E has side effects. So from sigma, I go to sigma prime, right? So as I do the entire F, I have to go from sigma prime to sigma double prime. No, this is a function definition. I'm very sorry. We're not executing any function. We're not executing any function. I'm completely on the wrong track here. So what happens? This guy has to evaluate to a function f, right? This is a functional expression, right? It has to evaluate to a function f. So we're starting from sigma. Obviously, we're going to end up with the same sigma because there's nothing changes, right? We're going to end with the same sigma, and we're going to end with a functional value f, right? So how do we define this f? Right? So when we're going to be executing f, we're not going to have this sigma anymore. We are defining this f with this sigma here, but when we're going to be executing, that sigma is not going to be there. We don't know when we're going to execute it. We might execute it, we might never execute it, we might execute it many times, right? So when we're going to execute it, let's assume that we have an assignment, or a store sigma prime, right? And it so happens that the denotation of f and v with sigma prime is this pair v prime sigma double prime, right? Let's assume that that happens. The added condition is that if I take this sigma prime and I take an environment where x maps into v, right, the denotation of E must be v prime sigma double prime, right? So I have to produce a functional value, right? This functional value, mathematical function, right? You have to think as a mathematical function, because what we know as functions take arguments into values, right? So mathematical functions don't have side effects, and we have to define them in a way that reflects the change that may happen inside here, right? So the functional value that I define will have to have sigma prime as an added argument, right? My denotation for a functional value has to be a function whose added argument is the store. There's no way around that, because the mathematical function that is my denotation doesn't have the capability of having side effects. All right? And what is going to produce that functional value? It can no longer produce just the result. It has to give me back also the store that this guy changes, right? So this is what becomes my denotation for the functional expression here, right? So what are the conditions that f has to represent? So let's assume that when it receives value v and sigma prime, then it produces value v prime and stores sigma double prime. For that to happen, there are some conditions that E, the expression E, the evaluation of the expression E must comply with, right? So what must happen is that when I execute E with this same sigma prime and with a binding for x in delta, I produce these two values, right? What's different between this guy and this guy? The bigger guy doesn't need a binding for x, whereas the smaller guy needs a binding for x, right? Otherwise, they're pretty much the same thing. So how do I go from the big guy to the small guy? I put a binding for x here, and the same computation should ensue, right? So if I don't have a binding for x here and I produce this, when I have a binding for x here and I execute E, I should produce the same thing. Clear? Yes? And remember the fact that we're not connecting the sigma and the sigma prime, because the definition, the store at the definition point is completely different from the store at the execution point, at the call point. Sequence. This one is simple. So it's the essence of the threading of the store, right? This is the one thing that threads the store but doesn't do anything to the environment, right? So we have no problem reusing the environment, but we have to thread the store, right? So I start from this guy, I get this one, which I have to thread into the next guy, and this is what I get for the result, right? So I execute E1, the store suffers all the side effects from E1, and then those side effects are passed on into E2, which adds further side effects and produces yet another store. Okay? This is the essence of showing that the changes of the store happen in sequence. The while loop. So again, a tough choice. What's the value of a while loop? We're not very consistent. We're saying that the value of the while loop is true. Right? Because it's easier, right? It doesn't really matter what the value of a while loop is, because we rarely use a while loop with the assumption that it may have a value, right? But because our semantics is that everything has a value, we have to give it 1, and we're picking true. Not very consistent for us. But yeah. So how do we execute this? So let's assume that sigma delta, under the context of sigma delta, E1 evaluates to false. And we're going to have several rules, right? So the first rule is let's assume that E1 evaluates to false and sigma prime, right? If E1 evaluates to false, the while loop doesn't execute at all. All right? Because it doesn't execute at all, the only side effects that we're suffering are the ones from executing E1, right? So when we execute E1, we go from sigma to sigma prime, right? This while loop will never execute. We evaluate E1 is false, right? And we jump right to the end. So what are we going to get at the end? Whatever sigma we had at the end of E1, which is sigma prime, as it is here, right? So that's case 1, right? When the condition is false. What if the condition is true? So this is going to be the interesting one. Okay, so so to give you some context, if I have a while loop, E1 do E2 end, right? So this happens to be perfectly equivalent to if E1 then E2 inside of the if while E1 do E2 end if, right? Or end. Yeah. Which creates a bit of recursion. This is the perfect vehicle to define the semantics of the while. Okay? So obviously this is only interesting when E1 is true. So let's assume that E1 is true. Sorry. Let's assume that E1 is true. Right? And as we evaluate E1, under the side effects, we obtain a store sigma prime. We, of course, thread this into sigma prime, and we evaluate E2 and get a store sigma double prime and the value V2. All right, which actually we don't care that much about. All right, and then by executing while, by executing this, the very same statement that we're executing here, right? But starting from sigma double prime. And this is very important, right? Because with the sigma here, E1 may be true, but with the sigma double prime here, E1 may no longer be true, right? So starting from sigma double prime, doing this entire statement, it's like a little bit of recursion, right? We obtain a sigma triple prime. Then guess what? Right? What's going to happen in here? Right? So this entire while is equivalent to E1, which we know it's true, E2, while E1 do E2, right? End. So under the assumption that E1 is true, this statement and this statement will necessarily produce the same results, right? Clear? So this is what I'm taking advantage of, right? So I have sigma here, I have sigma prime here, I have sigma double prime here, and I have sigma triple prime here, right? So this is what we have. Sigma goes to sigma prime goes to sigma double prime, sigma double prime goes to sigma triple prime, and since this is equivalent to this, whenever I start from here, I should get this guy. Cool? Yes? All right. Next step. Right? So in any language where we declare a structure or a class, let's stop here. Sorry. Let's stop here. This is a good place to stop.